record. I finally published the previous community call on YouTube. I had like I was back by two. So there is the number 11 and 12 that are now on YouTube. You can rewatch to relive again those nice moments we have together. And yeah, okay, let's start. I will share my screen. Uh, Okay, can you see my screen?
Yes.
Firefox browser. So, welcome to Community Call 13. Today, we have not a lot on the table. Basically, we have the release of the previous of the work of the past 2 weeks, and a presentation by Ben on SNOS, the SnarkNet OS. So what did we achieve this past week? A bunch of things, as there have been some fix on the price. I think the fees paid for the transactions. There have been a bit of refactoring of the code moving around. There have been a few fixes, and people are still working on their on the layer 1, layer 2 track. We have the first pull request merged to the feature branch. If you want to see the current state, it will be here, I think. Layer 1, layer 2, and other people are working on the StarkNet OS, the SNOS that will be presented today. So yeah, that's it. Good job, everybody. It went fine. And regarding the issues that are available, I'm really pleased because basically all of those are taken by somebody. We have 11 active contributors, and
We can see the board. I
yeah,
don't know the oversee, but I personally see just the community call.
sorry, you see the community call?
Could you show the board maybe with the task?
Yeah, that's what I'm showing you. It's not shared. Okay.
Maybe it's just me or
Oh, maybe.
No, can't. Even I was seeing the community call. Yeah,
okay.
I can see it
Okay.
now.
Better.
Okay. So what I was showing is the release number 4 with the changelog, the layer 1, layer 2 messaging, which is here, and there have been a few commits on it. The first few commits, so it's going pretty well. We now have like the data structure and the logic required. What we will need to add is 2 threads in the client, one which is listening to Ethereum and then putting the layer 1 messages in the pool when he receives some from the StarkNet contracts on Ethereum, and another which is doing like the opposite things, which is listening to layer 2 block production and then creating a transaction to commit this data to layer 1. So this will be like the next steps. And I was saying that I'm kind of pleased because basically every available issues that is ready to handle now as a contributor. So we have probably 11 there, and there is the other working on separate tracks. So we have like close to 20 active people working at the same time on Madara. So it's quite impressive. Thank you, everybody.
There are a few stale ones though. Like I'm thinking about the LRU cache one, the get state update one. Yeah, how should you proceed with these ones where the contributors do not have any?
This one is working on layer 1, layer 2 instead. So maybe we can put it back in the pool, and somebody can start back from where it was. And the other one
was the get state update. I don't think Pierre is working on.
Get state update. We are waiting on Lana, I think, to provide the runtime API to get state update. So I don't think the contributor is it's the contributor, but I think it's on our side.
Okay.
I will check with Lana after this call. So yeah, that's it. So probably next week will be full of feature merge. I hope so. And no,
there's also your refactor of the CLI, so we can finally run the test within the CI, because that's been a kind of a blocker right now. Not being able to yeah, we had to be careful with merging PRs and just adding new features because of that. Can share maybe about how you did that? I think would be interesting.
Oh yeah. Okay, I will share my screen again and we will look at my pull request. So basically we did previously we moved our RPC test from JavaScript to Rust, and then we had them and it was working, except that each test, so each Rust test was spawning a new substrate node. So it wasn't really effective in terms of performance, and it took a lot of time to run in the GitHub machines. So I did a refactoring, here it is, to have them run on a single node. So the assumption is that there is a Madara node running on the background on your machine, listening on port 9944, which is the default substrate port. And what I did is that I removed the whole logic for
running the node. It's not running the node.
Yeah, for spawning a new node. The only thing you spawn when you create the Madara client is a client, but it's a request client. Request the RPC library, so you can send RPC transaction. And the big idea is that there is two types of interaction with this client in the backend. There is a read and write action, and we can read, it's just like reading stuff from the chain, and write will be putting new transaction and minting a new block. So we can run as much read operation at the same time as we want. There is no problem with this, but we don't want different tests to be sending transaction and minting a block at the same time, because it will mess up the transaction orders, the block state, and the thing we want to verify. The flow most often is we create a transaction, we mint the block, we query for this block, and then we check that the transaction actually did what we expected it to do. But in order to do this, we need that no other test is making the chain move forward at the same time. So there is a feature in Rust that does exactly this. It's the read-write lock in Rust. It allows at the same time either multiple reader, any number, or one single writer. So what I did is that I created one Rust instance of the structure that allow us to query for the node which is running in the background, and I've wrapped it in this read-write lock, so that, and then I hide so I declare the method that submit new transaction or new block as requiring the object as mutable, so that you can only acquire them and use those methods if you acquire the write lock on the read-write lock. But on the other hand, as many processes as you want can acquire the read lock. So in practice, it's in the fixture. So the fixture to get the Madara client, thread safe Madara client is just a wrapper around the Madara client inside a read-write lock, and there is like two methods. Get the startnet client, so this is the read one, and there is a write which will acquire the internal lock. And now if we want to write a test, so get class, it will be really simple. There will be only read. So you query your RPC client and then you do your call. There is no problem with this. But now let's say you want an invoke transaction. So you get your read client, this doesn't change. But then if you want to create a new transaction, which is what is happening here, you have to acquire the lock. So you call Madara write, you await. It's not exactly this structure. Instead, if it's async lock rest, which is basically gives the same property, but instead of locking the thread while you are waiting, it's done in an asynchronous way. So if one thread is blocked, it will just do nothing, and the CPU will be free to compute other stuff that are awaiting during this time, and then it will loop back to check on it instead of just waiting, doing nothing, and spending time doing nothing. So this is a small optimization. And so what you do is
it could have worked with a normal RW lock. But
it was working actually. My first my first try was with this structure, and it was working, but there is a Clippy warning about this kind of things, which tell you that you are acquiring a mutex lock inside an async context. And basically what it will do is that it will block the whole async server, because all the async thread, async tasks are run on the same thread, the same system thread. So when you acquire this lock and you are waiting, you will be locking the whole Tokyo server because it's on one single thread. So you just like destroy the whole purpose of using async, because you are not executing stuff while you are waiting, you are just doing nothing. So there is this warning with Clippy, and after some research, I ended up on this lib, which contain mutex, RW log, semaphore, and barriers. So a bunch of utility methods that are really nice and really convenient. I just had to change the import and add await everywhere I was using it instead of unwrap, and it was working out of the box. So it was really handy.
Wait, so Tokyo manages all of the threads it spawns in one OS thread?
I'm not 100% sure, but yeah, I think that the async server is executed on one thread, and then it's creating tasks, which are green thread. And those green thread, they are all handled by the same Tokyo server, which is monothread. A bit like the event loop in JavaScript. So yeah, that's my understanding of it. I may be wrong, but that's
with this setup, we can, when we are running the test now, we still have to specify that we only want one thread, or we can run them in parallel.
No, you can run them in parallel, and that's actually what's happening. I run them without like the one thread things, and so the the drawback is that well, the order is non-deterministic, so we cannot check things like block number, block hash, because the block hash contains its number, or transaction hash, because the transaction hash contains the nonce of the account, and the same account is used for a lot of tests, so you don't know which will be executed first, so you don't know which nonce your transaction will have for this.
Maybe we shouldn't run them in parallel. I mean, I don't think it's a good. Yeah, I think it's better to have. I don't know.
I don't think as a real.
I think it depends a
drawback.
bit on the test that you want to run. Actually, there are some tests that you don't mind running it like this. Or there are other tests that you might want to run sequential.
Yeah, maybe. Yeah,
And
probably.
we can later have an option, like this was for one of the services that we were internally writing at Pragma. So like what we did was like a similar thing, but like you have an option to clear the state of Madara. So like most of your tests run in parallel, but then like for whichever test you want to start from a blank state, like you have this function which will probably start Madara again or somehow clear the entire state.
Oh yeah.
So we can
But
test
the
those things
thing
over
is
there.
that function works while Madara is executing.
Well,
Sorry, I didn't get the question.
It does it? I don't know. I don't know. I'm asking.
No, I didn't get the question.
So the thing is, we have a Madara instance running, right? And we run some tests. You were talking about the function that clears the state, but the thing, my understanding is that you need to reset Madara for you to reset the state. So it's more like you shut down the node, then you call that substrate function, which clears the state, and then you run it again. And if you are
Probably, yeah,
doing
it
that,
could just be
create a
like
new
starting a new Madara node either. Like, I don't know, like we could do anything over there. Maybe have a function in substrate to clear it, or maybe just like stop the node and rerun it. Like have all these tests that run in parallel, and then like have these specific like tests in which you want to check the transaction hash and block number and everything. Over there, we could do this thing where like what we were already doing, like have a new Madara node for each test and they run in like one thread.
Yeah, the only thing about that is in terms of running it on your machine, I agree that you can do that. But if you're running on CI, you actually want to do two different runs, one that runs the one test and the other one that runs the other test. So you don't need ever to clear the state between, because you are running two separate jobs and you can run them in parallel because they are running in different images.
Yeah.
Okay, that can. So you mean like for those tests, like each of those tests is a different job then?
You can run it in separate jobs. So you say, so I want to run the ones that I need to be sequential in one.
Hello?
Okay, I lost your audio.
Yeah.
Yeah, we can't hear you, Oak.
Oak, we can hear you.
I don't know, can you hear us?
Doesn't look like it.
He was about to reveal the secret to run tests in parallel on GitHub. They had to shut him down.
He doesn't know what's
Admitted
happening.
he's Satoshi. We all
What happened here?
Okay, he's back.
I'm back. All the sound was passed to Microsoft Teams. I don't know. What happened there?
We lost your voice. Like, can you say what did you say again? I mean, like we lost the complete
So
last thing that you said.
where did you stop hearing me?
So you were talking about running each test, I think, in a different job or something like that.
Yeah, so the thing is, the ones that you run sequentially, you can run on one job, and the ones that you don't care about the order, you can run on another job. That's it. Just that.
Okay, yeah. Got it. Okay, yeah, makes sense.
Yeah.
So going back to the code, and it will be important for people that want to add other tests. The idea is that you acquire the lock here, which means that from this point, no other test is allowed to write or to read anything from the to write yeah, to write or to read anything from the node, from the Madara node. So to call this kind of function. So you kind of are the only one at this point to be able to interact with the Madara node. So you are free to do like anything you want, like creating a block with transaction. And as soon as this variable is dropped, the lock is also dropped, and you will release the lock, and other tests will again be able to query stuff or to create other blocks. So the idea is that you want to hold this lock the less amount of time possible, the minimal amount of time possible. So a good practice is that if you want to create a block, then query stuff to check that it worked, what you will do is, rather than doing your queries while you hold this lock, what you will do is just get the block number. So you do one query, and then you release the lock here. And afterward, using this block number, you are free to do as much query as you want, and those will be executed in parallel with the other test. And they can be heavy computation. It's not a problem. You already released the right lock, and any other test can acquire it and do it and run its own logic. So you really want to avoid like heavy unnecessary computation from the time you acquire this lock. And you also have to be smart, because you saw I called block number here, while I still have the lock. But if I release the lock and then call block number after that, I have no guarantee that the block number I will get is the one where that I created a bit earlier, because maybe another test will acquire the lock and create a new block in
That's
the
why I
meantime.
think we shouldn't run them in parallel. Like, it can create a lot of these like very weird scenarios. But yeah,
Well, it works well if you know what you're doing.
yeah, that's true.
But yeah,
The thing is if we start getting errors there, it's going to be really hard to reproduce them. So if the thing is, if we don't get errors, it's fine. But if we start getting errors in the CI, we need to change that to be sequential, to have reproducibility.
yeah, I get your point.
But right now, I agree with you. We can just leave it as it is and run it like this. If we start getting lots of errors on those tests, we need to change it to be sequential.
Yeah, I understand. But you can still run them sequentially, debug your errors, and then for the CI, execute them in parallel.
I'm just
No,
saying
but
if we have those errors in the CI,
Yeah,
because the CI is our source of truth if we are having errors on the integrations or not.
yeah.
So if we have errors there, we need to change it on the CI to be sequential.
Okay.
Yeah.
but to what you were saying, Timothy, like the errors won't happen if you like run them sequentially. It's like sequentially everything works fine,
Yeah.
but like parallel it breaks.
The thing is, errors might occur if we run it sequentially, but that way we can reproduce the errors because we know that it's running in that order. The thing is, if we just have errors and we are running it everything that we don't ensure any order, yeah, you can't reproduce it and you can't debug it. That's the thing.
Just one thing over here. So like you do everything inside that block. So like after the block, the lock is automatically released. Is that how it works? Like when it
Yeah.
goes out of scope, it just released.
Yeah, exactly. It goes out of
Okay.
scope, and so drop method is called rest drop. When a value goes, yeah, that's a video game.
Okay.
when the value goes out of scope.
Scope and then it's
Drop.
dropped. Okay.
Yeah. So
And
the
we do we like I couldn't find anywhere we use Madara.read. So we don't really take any read logs. We just use the RPC to read.
yeah, the read is done through the get starknet client. But yeah, there is no really
Okay.
lock on read actually.
Like how do you like how do we stop it from writing if someone is already reading something?
It's done within get starknet client, I think, if you go in it.
Yeah, it's in the fixture. Yep. So here you acquire the read lock.
Okay.
Here you get the
got
right
it.
one, the right lock, and here you get the read one. And once you have the lock, you do the get darknet client. But
Got it.
I'm thinking that maybe this is unnecessary, and we could just have one lock on write and still being able to read at any time. Probably it will still
No,
work.
but that could it could cause inconsistent. Could it cause inconsistent states?
I'm not even
Because
sure.
The thing is, if you have a write lock, you can't read. That's the best practice because you
that
don't know
makes
if
more
you are
sense to
reading
do
before
that.
or after the write.
But the thing is, this get starknet client, it return you like a structure that you are owning and you keep it. So it's not a referent. You keep owning this structure after the lock is dropped actually, because the
Wait, then
lock. So it's kind of useless, I think, in this implementation, because your read lock, it's only hold during this part of the code, and then you get your starknet client and it's your own entity. So there is no actually exclusion. So this part is kind of useless, and probably we can just go with
no, but this could cause some errors, right? Like let's suppose I write a
causes
test case.
inconsistencies for sure. Yeah.
Sorry, what?
Because if it's what Apurva was saying, that causes inconsistencies for sure. Because if you acquire a write lock and you do a read in between, you can't ensure what is going to be the read result.
Like for example, let's say I write a test case to read, like I transfer something to account A and then I read the balance. So I transfer something to account A and now I release my lock.
Yeah.
Then someone else takes the lock and uses the funds of account A. And then I read it and I get an unexpected number from what I like actually, because I had no lock for the read part. So now like I'll get some unexpected number. Does that make sense?
The thing is, you will read the amount on the account at a certain block 8. So you are always passing like which block you want to read. So
But that's just on the implementation side, right? That you're just expecting everybody to get the block and release.
Yeah. I think that's not perfect. Yes.
Plus the other write could also happen in the same block technically. Oh no, you would make sure the block is already created. Okay. But yeah, like that's more on the like it's like something that's working like coincidentally, but like shouldn't have probably
Yeah. It's
Okay, sorry. So like in that case, would it require that means you need to get the block ID before releasing the lock, right?
Yeah,
so
exactly.
that you can know the particular block you're making the call to.
Yeah. Yeah, you
Okay.
need to get the block ID before you release the write lock, so you can know which 8 you on the chain you want to call for. And if you do this, it's work. Fine.
Okay, makes sense. Thank you.
So yeah, that's basically how it works. The pull request is still open. Feel free to add comment, to review it, and please.
And so we finally be able to add the coverage back in the CI. Next week really we have coverage back, and we also have a Gomu in the CI. but that's the bug that Oak needs to look into, or someone. Is there someone still working on Gomu Gomu, Oak, or just you?
So the thing is that integration was not done by me; it was done by Berra, but I was helping him along the way. The thing is, the integration is all finished. The only thing that is failing is the verification of the transactions inclusion in the block. So what Gomu Gomu does is it shoots lots of transactions, and that it verifies if the transactions were included in the block. And the thing is, I don't know why it's taking a huge amount of time to do that verification.
What do
And
you mean
that's
by how does it verify it? Like
it looks for the transactions within the block, I think, but I'm not sure about it. I need to go check the code on how it's done.
okay,
Yeah.
okay.
That's the part of that I was saying that I still need to go debug it.
Okay, and is there anyone else working on Gomu Gomu? No.
Nope, not right now.
Okay. Yeah, I guess it would be great to find someone. If there is anyone that wants to work on it, we can probably ask in the group. Look for someone to lead that effort there. Yeah.
Yep.
Okay.
I think Oak is leading the effort on Gomu Gomu, and if he need help, yeah, he can find other people.
Yeah. Yeah. Um, just I was checking here the pull requests. Do you know how much time does it takes to run the tests currently, the integration test?
The RPC test,
Yeah.
it's really quick. It's like less than 20 seconds, probably.
Oh, boy. That's cool.
On my computer.
No, on the CI.
On the CI, I'm not sure.
Is it sending?
Just just because the integration sets it's run on all the PRs and people usually are looking into that before doing
Yeah,
new PO,
it took
new commit.
on the CI, it took the run RPC test step after the setup job, the checkout, everything. It took 2 minutes, and
It's fine. That is fine. If it's 2 minutes, that's okay. That's totally okay.
and I think a good part of it is actually compiling the test, maybe. But yeah, 2 minutes.
A big part of it is it's compiling everything. Yeah. I'm more. I actually tried to cache it on the build because the build we are using a big machine there, so we could do it faster. But the thing is, then we can't retrieve the cache because of the build size.
Yeah, it took
The
1
machine
minute to build the
Sorry?
test.
What?
I say it took 1 minute to build the test and then 1 minute to run.
No, then it's fine. If it's those timings, it's fine. It's okay. We are fine.
Okay.
It's just because the last time that we did a refactor on running the integration tests, it was taking like almost 40 minutes or 50, and
yeah,
that is not feasible.
Yeah.
Yeah.
Okay, so let's move to the StarkNet OS, I guess.
Yeah.
Yeah, I don't know, Ben, do you have some slides, or should we go through the
I think
document?
maybe we should handle it like this. So yeah, so just in general, we're working on the StarkNet OS implementation in Rust. This is going to be executed via the Cairo VM in Rust, whereas today the canonical stack is executed with the Cairo VM in Python. I'm predominantly working on this with the Pragma guys on the call. So I think maybe the way we should handle this is I show how the integration affects Madara or should affect Madara. And then we can go into Matthias's document, and then maybe we can look at some of the code right after that.
Yep, sounds good.
I have a question, something we need to explicit. So if I understood everything, the sequencer running the virtual machine, it's it's like the fast track to execute, but you cannot prove this. So in order to generate a trace that is receivable by the prover, you need like an heavier execution, and that's what the StarkNet OS is doing.
It's not a heavier, I mean, it is technically a heavier execution, but I would say more so it is just it is applying the transactions in the block to the state in a provable way, just so that we can prove it. It happens to be heavy. But
basically, if we were to do ZK to like, yeah, to ZK, snarkify the blockifier, like in some way, it's like, yeah, you need to write the blockifier logic in a provable way, and that's done through a Cairo program, which is called os.cairo. Yeah, and it basically does exactly what the blockifier does, but in Cairo. That's like the hard part, and it's mostly hints, so it's not Cairo really. It's a lot of Python behind the hood, and that's why we're writing everything in Rust, because otherwise we couldn't use the Rust VM to run this program, and we would have to use the Python VM. That would create a lot of like interdependencies within Madara, but yeah, then we will show that.
Another fun little caveat for newcomers is that it's Cairo 0, something that maybe a lot of people haven't even seen, but the old kind of rough version of Cairo. But yeah, we'll go over some of it. Right now I'm going to show you guys, I want to show you just where this all slots into Madara. So we had a joint effort with the Avail team, the Celestia team, and us to put together kind of the initial foundation for a DA kind of framework. That currently lives on the client side, so it's in client. Can you guys see my screen?
Yeah.
Yeah, okay.
Yes, we can.
Client DA. So client DA has a library in here. So it runs two, the client, when it spins up, it spawns 2 tasks. One of them is a prove task, and one of them is an update state task. So there's some comments in this prove task in here that go over where the StarkNet OS needs to slot in. So right now we init this DA worker in a context that is a sovereign rollup. It's actually misnamed in here, which I didn't think about, but we have it named in here as a validium. It's actually initialized in a sovereign rollup context, which means there's no validity concept of validity. And when we say validity, we mean that the execution of this block is being proved somewhere. So a sovereign rollup would just be, hey, this is the state changes that occurred in this block. And that's the way we have it right now. So we have these DA modes, Validium. There needs to be another one added here, which is sovereign. So Validium, volition, and validity. Validity is the way that the current canonical StarkNet executes. But yeah, so we'll go in here. This SNOS will basically supplant this logic for any context that's not a sovereign rollup. We don't need to go in and manually index into the MPT and get the state changes. We can just run the SNOS. So the SNOS will effectively do that. Or we actually need to format the input to the SNOS that does this. So that was a little misleading, but anyway, the SNOS then runs that proof in a Cairo context, in a provable context, that yes, indeed, the transition of this block full of these transactions applied to this state does indeed give you an output. That output is the DA that's actually written to L1. So right here within the validity, within the context of a Madara that is initialized with a DA mode of validity, and eventually this will also be validity, volition, and validium, we will run SNOS. And so what is SNOS? I'll let Matthias talk about that.
Yep. All right, so let me share my screen. Can you see it? Okay, so I've done this small, relatively small HackMD document that goes through. It gives like a high-level overview because the OS is a very, very big Caro program. But I try to go through like the major steps, explain a bit how the major hints work. And that will serve as it's like an evolving document. It's not like fixed and will be updated as we progress with the StarkNet OS implementation. As I said in the beginning, the intro, the StarkNet OS is really just one Caro program, not a StarkNet contract, but a Caro program written in Caro 0. And yeah, so you can, and that's basically, the program hash of this OS is the one that is registered on L1 on the StarkNet core contract. So that's in the context of L2s. In the context of L3s, you could imagine there would be some StarkNet core contract on StarkNet, and that will have the program hash of the StarkNet OS run by the L3, and that's this program execution that's actually been verified. When we say that we verify a proof, it's the proof of execution of this Caro program and nothing else. So that's pretty simple diagram of what happens. So the OS is run for every block. That's actually not ideal, especially with Madara, where we have very low block times. That's definitely something that will need to be changed in the future. It's not compatible with for very low block times, but for every block, it follows these steps. So first, we load the OS input. So the OS input is basically this Python class. It looks like nothing like this, but it's actually huge. And like the most part is getting this input. It has all like the state commitments, which classes have been interacted with within this block, which contracts, the mapping between class hash and compiled class hash, the config of StarkNet at this block, like the maximum number of steps, this kind of things, the transaction of this block and the block hash. So that's the input that's being loaded into the OS. So that's the first step. Then we do some pre-processing. So by pre-processing, we mean, where is it? So we mean getting, okay, here it is. We mean doing a bunch of stuff, like especially there is an internal mapping that the OS keeps between like the block number and the block hash. So yeah, we update this mapping, we check that we're consistent, we're not out of sync. So that by out of sync, we mean that we're proving the next block in the sequence. And we basically, we update this mapping. That's like the main thing that is being done here. And that's also where we specify this block hash buffer. I think that's like a very interesting thing, but on StarkNet right now, there is a block hash syscall that I think has recently been added, but you can only get the block hash from like the last 10 blocks. I mean, you cannot get the current block hash, but you have like a 10 blocks delay. And that's because of this. That's because we need this buffer, because proving this program running this OS takes a lot of time. And so here it's hard coded to like 10 blocks to let us the time to actually run this program and make sure we have updated the mapping and done all the pre-processing.
It's also that the Starkware infrastructure, in the Starkware infrastructure, the StarkNet one, if there is more than 10 block of difference between the sequencer and the prover and the StarkNet OS, the sequencer stop until the StarkNet OS catch up with the sequencer.
That's a good question.
Yeah, it's something I learned talking to people at Starkware internally.
Okay, so I think it makes sense. It makes sense because of this buffer, and the OS will fail running if like this it's not in sync anyway.
This is not something we can easily do with Madara, I think. Like it will be
yeah, anyway, the OS will need to be tweaked to work with Madara because of this low block. I said like it will need to be tweaked in some ways that I'm not sure exactly yet, but definitely
that interface between the actual implementer of SNOS and SNOS is going to be interesting. There's going to be some shared state that SNOS and Madara or whatever is calling SNOS are both aware of. But that's yet to be defined, I guess.
Yeah, that'll be very interesting. Okay, so after the block pre-processing, which is like not the most interesting part. So yeah, the block pre-processing, I won't go, if you want to like go into details, feel free to read the document, but there are a bunch of things like this thing called the execution helper, which is there are a bunch of like classes that will help us later execute the transactions, make sure we keep like the good view of the state at each point, at the specific point in time. And that's what Ben was saying, is that there needs to be the sequencer needs to be aware of what the OS knows in some way to be able to keep in sync. And we will need to figure out how to do this in Madara as well, probably by reusing the substrate storage layout. Using the substrate storage layout to run the StarkNet OS. That's for later. Okay, and then the main part is like exactly as the blockifier is doing, running the transactions. So really we have like an execute transactions function written in Cairo. So I can maybe show it. Okay. OS execution. Yeah, here it is. As you can see, it's quite large, but it's basically doing the same as the blockifier. So it checks the type of the transaction here, and based on the type, it executes it differently. So we also do the same in Madara. We just pass the block context, execute the transaction, check also for the gas, and charge the fee at the end. So really, it's exactly the same thing, nothing different. And it's also something I've been wondering and talking a bit with Ben and Lucas, like how the StarkNet OS like needs to be doing exactly the same thing as the sequencer, otherwise like everything breaks as far as I understand. If like some parameters are different, or like we're executing a bit differently, or like charging the fees differently, I think like everything will break, and I don't know how Starkware right now is making sure that does not happen. I don't know if you have some insights on this, Ben, maybe.
Yes. I mean, there's a pretty extensive test suite for the OS, and the test suite for the OS is all dependent on the actual Cairo version, because as we hash all of these programs and as we hash all of the execution states, we hash it with the version of the Cairo compiler and the Cairo toolchain. So that's why, like, when we go into the code a little bit today, I have a suffix of most of these things, and it's 0.12.2, because all of the current test suite that we're trying to emulate is very dependent on the toolchain being 0.12.2. I'd say that's the best. Maybe it'll look a little clearer once we get into the testing of it, but I mean, that's kind of the best I have for you.
Okay, thank you. Okay, so after executing the transactions, again, like everything is done through hints. Hints are written in Python, and that we will need to rewrite in Rust. Although like writing these hints is not the hardest part. The hardest part is rewriting the whole Python code. That's like the Python code that's behind this business logic thing. Like we have a bunch of things like the Merkle trees. We'll go into the code later, you will see, but the hints themselves are not like that hard, like managing the VM scopes, managing how we handle dictionaries, pointers. This is really not the hardest part. Okay, and so the execution, transaction execution is in 6 steps. We validate the transaction version, we compute the transaction hash, we check and increment the nonce, we run the validate endpoint, we execute only the non-reverted transactions. That's actually important. And finally, we charge the fees. Yeah, there are some mysterious hints, as I say, like this one, which I'm not even sure what it does. So we still have things to like learn and discover about how the whole OS work. Yeah, and then finally, so once we've executed all these transactions, we can perform the state update. That's what will be the output of the StarkNet OS, actually. So we start by initializing the dictionary of state updates, and we fill this dictionary. So in 3 steps, again, first we update the contract state trie, then the contract class trie, and finally we compute both the initial and the final roots of the global state. That's actually something I've asked here to Lyre, but he didn't understand quite the question. But the OS does compute for each block, we're computing the initial root and the final root of the global state, which I think do not make a lot. I mean, I don't see why we're computing again the initial root, whereas we could, I don't know, pass it as in the input or through a hint or something. So yeah, I'm still trying to wonder why this happens. And there are a bunch of things like this where I don't know. Yeah, if maybe someone has an idea why that could happen, let me show the code. Yeah, here we compute both the initial and the final roots of the global state, and we return it. And I don't see why this is not like passed through the input, because we know for sure what's the global root at the previous block because we already like computed it. So I don't know.
Yeah, good question.
Maybe we can take it offline, but what was Lior's answer? He just didn't understand.
Yeah, he didn't understand.
Yeah, we should look at that.
Do we, because like since all this code is basically the blockifier and the VM, so whenever like Starknet is launching a new transaction version or like any new update, are they actually like updating the OS code and updating the hash on the verifier?
Yes.
Like, is this OS code like updated regularly?
I mean, if it applies to any of the execution of the OS, not inside an internal hint, then yes.
Okay, got it.
Yeah. Mostly when we talk about Starknet upgrades, it means that the OS has been upgraded.
All
Because
these even like
otherwise-
12.1, 12.2.
Otherwise, the facts won't match up. So like the fact at the end of the day is the program has the OS with the output of what the OS outputted, and that won't match what's been verified.
Yeah, makes sense.
Yeah. And finally, once we've computed these, so the contract tries, the contract class try, and the roots, we update. We update the different Merkur Patricia tries. Yeah, and that's also a question: how do we want to like re-implement that? Yeah, because right now all of these Patricia try implementation is done in Python. Yeah, so we both have Peterson Patricia tries. We have Poseidon Patricia tries. There are specific constants for the tries, and it's actually done in a very clever way, which I don't fully understand, but like it uses some pre-image to like speed up the computation. Yeah, I haven't looked that deep into it, but it's quite clever. And yeah, that's pretty much it. Yeah, in a nutshell, that's all it does. It's a lot of things. Basically everything that the sequencer does, plus computing the state update and updating the tries, which we don't even do within the sequencer. So as a conclusion, I wanted to say that diving into the StarkNet OS is not only interesting to like understand how StarkNet works itself, but it's also very interesting to later on like tweak the OS, because if we want to really have custom app chains, to have like custom like customize a StarkNet app chain, that's where you can get the most out of it. It's by tweaking the OS itself. If you just tweak the sequencer, it won't work. You need to change the OS, as we said. So blocks batching is, I think, the first thing that will be interesting to look at. How can we run the OS on a batch of blocks instead of just for every block? And that's actually very, I mean, it's we have to do it for low block time app chains, and it actually will reduce the cost a lot. Let's say you compute, let's say you run the StarkNet OS every 100 blocks, then all the state update that happens between these 100 blocks are not, you don't pay for them. You just pay for like the state difference between the first block of the batch and the last block. And that's actually, I think StarkNet wants to do it at some point as well. Yeah. The state representation as well. We could experiment with different state representation instead of the Merkle-Patricia tries, maybe binary tries or Verco tries. I mean, that could be a lot of different ways to represent the state. And yeah, that's within the OS code again that it should be modified. The fee model as well, we saw that the OS is actually charging the fees. And if we want to, let's say, make a free StarkNet, we could just remove that or change completely the fee model of the app chain. That will also be done through changing the OS. So that's just like a few ideas, but I'm sure there are a ton more. And the more we will be able to understand how the StarkNet OS work, the better it will be.
Okay. 100%. To touch on that, one of the cool separations of concerns is that the sharp and the prover side just take in the StarkNet input as a Cairo job. So the sharp is agnostic to the state of StarkNet. It doesn't know anything about StarkNet. So that means that on our side, on the SNOS side, you know, we can basically make a lot of these optimizations and interesting feature sets, as long as we're, you know, proving what we need to prove and we output a trace. You know, it's not going to affect the actual proving side of it.
We could even have like, I would imagine like some things like a mini StarkNet where you don't even have like declare deploy. You just have like invoke of like specific predefined transactions, like for micropayments, for instance, these kind of things. Like they're like very interesting use cases to just to just have like way more concise versions of this OS. And yeah, exciting to see where this goes. But first, we need to dive into the code.
Yep. Yeah. And so, yeah, to go on top of that, I think there's a lot of greenfield design space for this to go. But what we're starting with is basically a one-to-one representation of what StarkNet does today. Let's get that business logic implemented into SNOS. So to go over that, there is an unfortunately closed source test suite of the StarkNet OS that I'm trying to push to get open source. But I am trying to since I have eyes on it right now, I'm trying to implement it in SNOS, and then basically we can open it up to all the rest of these cool innovations. But let's look at some code real quick. How much time do we have? Oh, are we 3 minutes past?
I think we can go. I
We
don't know.
can go as much as we want.
To the end of the night.
Cool. Okay, cool. So SNOS is here, keeps darknet strange, SNOS. It's still in active development. I think what we would love to do is to have like a big push maybe next week to get the testing environment in a good spot and then onboard some contributors. But we can take that offline. The way that it's currently set up is that there are a whole bunch of contracts and dependencies that need to be set up before the OS runs, kind of similar to the Cairo VM. If you guys have worked on the Cairo VM, there's a make deps script before a make test script, and it basically goes through and runs all the setup for the tests and compiles all the necessary contracts. So I'll show you just what that script looks like. You need to have a Cairo environment. Like I said, it's really, really important that you're dealing with the right Cairo environment. So if you don't have Cairo compile or StarkNet compile deprecated because we're dealing with Cairo 0, you'll see an error. We go through, we deal with the Cairo Lang repository as a submodule because it's mostly in Python. We basically can't have it as a Rust step, so we deal with it mostly as a submodule. This setup test initializes the submodule, make sure that you're in a context that you can compile Cairo code, Cairo 0 code, and then it goes through and sets up the tests. One thing that's interesting in this is that if you don't have your dependency path exactly right for or exactly the same for your Cairo code, you're going to get a different program hash. And the way these facts work and the contract states work is that you need to have, your program needs to be deterministically hashed exactly the same for you to get the same fact hash. So if we're going to compare this one-to-one with the StarkNet OS, we need to have the exact same thing. So we can't have any custom paths. So basically this puts a lot of our dependencies in the right paths relative to the Cairo Lang submodule. So here are our dependencies. I'll show you what that kind of looks like in real life. These are the contracts we need to run the test suite. Let's look at token contract. A better one might be dummy. No. Token for testing. Okay. So token for testing depends on Starkware, StarkNet, standard contracts, ERC20, ERC20. In Cairo Lang, the actual public repository, we don't have that subdirectory, StarkNet. Standard contracts, we don't have that repository. So in order to keep the same dependency layout, which means that we get to keep the same program hash, we need to set it up in the test script. So we do that here, make mkdir blah blah blah, copy the dependency there, and then compile all the files. So compile deprecated, all of the things we need. Okay. If you want to make a change to any of your tests, so we have the contracts here. If you need to make a change to any of them, you just run teardown tests. It's going to reinitialize the submodule and then take down all of the tests that we need. In order not to bloat the repository, we only ship with the StarkNet OS that does not have debug info. So this is the only artifact we ship with, build OS latest. It doesn't have any debug info. That's because in a production build of SNOS, this is the only OS you're going to get. When debugging it, we want the debug info. So we compile with the debug info, and all of the tests are run against. Sorry, one sec. All of the tests are run against this OS, which is a much heavier build with all of the debug info. Okay. So yeah, to the question earlier of like when something is changed in the OS, how are we absolutely sure that the platform isn't changing underneath our feet? This is the main test or preparation for the test that's run internally, and we're going to do the same thing. So basically, what we do is we set up an initial state through Blockifier. of a couple of contracts, a couple of contract classes. Again, those contract classes are dependent on the semantic versioning all the way to the final version. So if it's 0.12.3 compared to 0.12.2, the tests are gonna fail. And that's why these are prefix suffixed like they are. So we have initial state. So we deploy this. We deploy the token. We fund the token. We pre-fund the account, and then we deploy the account. That gives us our initial state. This is at block 0. So this is the Genesis block. And then all of the tests run on that initial state. So we have a pre-funded fee token and an account to use for the fee pair. This goes through everything we expect the OS to handle. So we have invoke declarations. I'm not going to go through everything, but if you do want to see it, it's prepare OS tests in the branch feature OS input. We basically run through a whole host of different things. This test contract is kind of, we have a similar thing in Madara where basically the test contract is built to facilitate the testing of all of the logic we expect to be able to run. And then we do so, we execute all of those transactions within the tests. So, deploy contract, set values, storage values, built-ins, timestamps, syscalls, call contracts, proxy contracts, L1, L2 messaging, L2, L1 messaging, implementation hashes of proxies, blah, 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 library calls, signatures, everything we expect the OS to do is done here. That's for the testing suite. As far as the actual OS run, so we have OS input built here. This is half the battle, which is basically just getting this in a state that the OS can run over it, and then also getting that shared state that we're going to have some sort of interface with whoever the caller of SNOS is, which is yet to be defined, but we'll definitely need the Madara team's input on. I don't want to go too far down since we're already 10 minutes over, but basically, this is a Cairo VM run of the OS that is compiled and shipped with the library with a layout that is StarkNet with Ketchak. This can also be StarkNet if you don't need the Ketchak built in, but we default to with the Ketchak built in. I'll probably end it there unless you guys have any questions. Okay.
It look hard.
It is tough. I'm happy to have Pragma with me because rolling solo was rough.
Yep. And there are a bunch of other questions. By the way, do you have any? I mean, we can take that offline, I guess. But yeah, there are a lot of problems around types, and I guess that's a more general question around the StarkNet. I was discussing again with Anshiro from Kazar Labs, right now the StarkNet Rust types are just a mess, and we don't know what to use, where everyone is using different things. And yeah, so here we again have the same problem, a new library, but we again have the same problem. We don't know what to use. We know that we can use the felt 252 type from the VM itself because we just interact with the VM. We don't really interact with StarkNet stuff, but yeah.
This is a path I probably don't want to go down, and this is what we're going to take offline after this anyway, but we can just show it here for now. So one of the easiest paths to the try that doesn't involve the SNOS team eventually basically building and maintaining a Merkle try implementation for the rest of our lives.
But I think there was one that Starkware with Lucas told me there is a Merkle partition try implementation coming.
Okay, then that'll be great. As long as I don't think the SNOS team should be doing that work. So right now it seems like the quickest path to implementation is using Pathfinder's try. It's pretty good. The only problem is that Pathfinder doesn't use the StarkNet API types. and they don't use the StarkNet API macros. So this is a path I would like not to lock down, but right now it is looking like we might need to, which is StarkNet to Pathfinder address, Pathfinder to StarkNet address, not ideal.
And what we did in Madara is copy pasting the Pathfinder implementation and changing the types manually.
Okay.
To work around this problem. So
Yeah.
we could do the same, but I agree that in both cases it's not great at all.
At some point, there will be like a single felt type. The repository is there.
Yes.
There is active development, but yeah, we will have to force integration down the throat of the repository maintainer. So this will be the hard part.
Yikes.
Yeah. But okay, one more reason to push this universal felt type forward.
Yeah, and not just.
I guess the question even after the universal felt type is that all of these functions and these functional macros that are done by, let's say, StarkNet API, they all wrap their implementation. So it's like, even if we get the felt type universal to everybody, we need to have the other utility functions.
Macro. Okay. Yeah. Okay.
But
okay. Well,
out of scope for this conversation.
Yeah. Thank you, everybody. I will stop the recording and see you in 2 weeks.